Just today? Maybe I'm just not paying attention. It's possible. I will begin. Dear Heavenly Father, we thank you for this day. I thank you for these students and pray you help them on the quiz, just do their best, that prepare them for the test, which is soon coming, and just that they would learn the most they can from this course for your glory, Lord. In your name I pray. Amen. Okay, so today I would like to talk to you guys about springs and springs with or without friction. All right, and so just my intention is to talk to you about the three different kinds of motion that are possible for a spring with or without friction, and then to try to solve the problem of resonance. Okay, that's what I intend for today. And so just to get started, as we've discussed before, we have mass times acceleration is equal to what? Well, it's equal to the force, the net force on the spring. And so the two forces we're going to consider are a velocity-dependent friction force and also a, Hooke's law, Kx, like this. Now here's a picture of what's going on. All right, so you got the mass over here. And here's the spring with spring constant K. And then I guess a good picture to think about is kind of like imagine it's in a vat of Jell-O. I guess cherry, maybe strawberry. What's your preference? I don't know. But it's got some kind of viscous medium, some sort of slimy liquid that it's oscillating back and forth in, right? And to a decent approximation, the friction force from such a situation is given by minus BV, where V is characteristic of the fluid in which the thing is moving. A good physical example of this, outside of attaching masses to springs in bowls of Jell-O, would be like shocks on your car. So how do the shocks on your car set up? There's a big coil spring, right, inside this tube. And what's inside the tube? Oil, all right? They put oil in there, and that oil is put in there to give a certain viscosity. And that's exactly this problem. It's a spring that's, being pressed with friction. And so by adjusting your choice of oil and spring constant, you can manipulate the kind of motion that you get. All right? All right, so let's see here. Something like that. So this problem, if we rewrite it, becomes mx prime prime plus bx prime plus kx equals to 0, right? So this is the mathematics that we have to solve to find x as a function of time, right? That's the problem of finding the motion of a spring under friction with spring constant k. So the way to do that then is this gives us m lambda squared plus b lambda plus k equal to 0. That's my characteristic equation. And that characterizes the solution. Right? As we've learned, there are a couple different cases. But, generically speaking, we could solve this with the quadratic formula, right? So this says lambda's what? Lambda's equal to minus b plus or minus the square root of the discriminant. The discriminant here is b squared minus 4mk, yeah? All divided by twice the mass. Now that makes sense because we assume that the mass is non-zero. Yeah, that seems like a fair assumption. Now, there are different cases then. I wrote that down, but generally lambda could be what? It could be real and distinct. It could be real and repeated, or it could be complex, right? So let's talk about those different cases. And here is where I need the book for terminology. So he says underdamped, or yes. So I'll start out with the interesting case in my view, which is when b squared well, excuse me, I think this is kind of the uninteresting case, but if b squared is greater than 4mk, right, then this gives us what is called, I believe, overdamped. The motion is said to be overdamped. Yeah. If b squared is equal to 4mk, we have what's called critically damped. And finally, if we have b squared is less than 4mk, then we have what is called underdamped or weakly damped motion. So let me just put in parentheses just a mathematical comment. So here, lambda plus or minus are in the reals. Here, lambda plus equals to lambda minus, again real. And finally, lambda plus or minus is alpha plus or minus I beta. It's a complex zero. These are the different kind of math we face, right? So let me number these cases 1, 2, and 3, yeah? So case 1, we're assuming that we have b squared is greater than 4mk, thus lambda equal to minus b plus or minus the square root of b squared minus 4mk over 2m. You know, these are, and I could, if you don't mind, I'm going to put a plus and minus there, yeah, to go with the plus and minus. These are real numbers, right? And we have x of t equals to what? E to the lambda plus times t, constant, right? Constant c1 plus some other constant c2, e to the lambda minus times t. I can be more explicit, right? I don't know if it's that exciting, but here's the explicit formula. C1 e to the what? Minus b plus the square root of b squared minus 4mk, all divided by 2m times t plus c2 e. This seems like a good place to use exponential notation, yeah? Minus b minus the square root b squared minus 4mk divided by 2m times t. You guys know the exponential notation, what I'm talking about? Instead of writing e to the x, maybe it's a bad choice. Instead of writing e to the, I don't know, star, we write exponential of star. These are just different notations for the same function in here. There are people who make a formal distinction between these two notations, but I am not one of those people. Okay. I just like to use exp sometime because it helps me to not write things as a giant, awkward superscript. Hey. Questions about this case? All right. 2, if we have b squared equals to 4mk, then that means that what that means is lambda plus minus are both equal to minus b over 2m. So x of t is c1 e to the minus b t over 2m plus what? C2 times what? Now maybe you guys can tell me. We have the repeated root case. It's the constant coefficient problem. What's the second linearly independent solution? X e to the lambda t is, your heart's in the right place, but t, right. So t e to the minus b t over 2m. How does she know that? It's just that she remembers the theorem that we worked out the other day, right? I would encourage you, this is a theorem that I wouldn't say you need to remember. I would say it's a theorem you need to know. Like, this question I just asked you, you should be able to like respond to without taking more than 10 seconds. Like, if it's taking you a minute to figure this out on the test, you will not succeed. All right. I understand you're not done yet. You're still working on this stuff, but that's something we should be able to do. All right, so that's the general solution to 3. This is the general solution to case 1, and then case 3. Oh, well, let's just take a second here. What does the solution look like? I start out at wherever I start out at, right? If this is x and this is t, just for the sake of picturing it, I start out at initial position x naught. How does x naught relate to C1 and C2? C1 plus C2 should be equal to x naught, right? And how about if I know that the initial motion has initial speed? Let's suppose that the spring has an initial speed of 1 or v naught, right? And suppose it's positive. So suppose that the initial speed v naught, right? What would the initial speed be? In other words, what's x prime of 0 equal to as it relates to the constants? I don't want to write those down again, but it would be lambda plus C1 plus lambda minus C2, yeah? Because you'd have to differentiate it. The chain rule pulls down the lambda. Oh, come on, guys. Don't really put a minus there. That's nonsense. That minus doesn't belong there. No, no, no. Look at that junk. Goodness gracious. Anyway. All right. This goes back to a comment I made the other day, which is if we're talking about physical motion, we should have exponentials with negative arguments, right? And if you look at this, you can figure out that both of these numbers are negative, right? So if it's got an initial velocity v naught, which is positive, suppose this is given, then roughly speaking, the picture should be something like this, right? It starts out, the x is still increasing, but what happens? Well, this is what happens, right? What happens as time goes to infinity? Like that, yeah? Something like that. And I'm not sure exactly how to picture this one. I'm never good at this particular thing, but this one also looks something, it might even do that. I don't know if it dips below the axis or not. It's possible it could dip below the axis because of the t term and the choice of constants. Like you could start out with x negative, and motion below the axis is possible because the spring could compress as it's cycling to 0 through the spring motion, right? But I don't know, that's about the most interesting that could be, something like that. All right? Case 3, though. Case 3 is really interesting. Weakly damped. So finally, we have b squared. We had, so less than mk. 4mk, rather. So we have, what was it, lambda is minus b plus or minus the square root of b squared minus 4mk divided by 2m, right? Which we could rewrite as minus b over 2m plus or minus the square root of minus 1 times the square root of 4mk minus b squared. And the reason I would do that is that if b squared is less than 4mk, that means that 4mk minus b squared is positive. Right? And if b squared minus 4mk is positive, then, yeah, what do I do? Oh, yeah. So it wasn't the, I have not butchered the inequality. I've just forgot to divide by 2m. Okay, that's good. I meant to multiply by 2m there. See, haha. I was just not done writing. Oh, no insult for that. Come on, that deserves an insult. Oh, you're thinking about. It was a non-audible insult. So you're just saying it's not that you had anything to say. You just now think less of me. That's so much worse. So much worse. Condescending. Oh goodness. Minus b over 2m. You guys are so mean to me. Plus or minus I. Oh, let's see here. I times parentheses the square root of 4mk minus b squared divided by 2m. Are we all on board for that? So the reason I did that is I want to write it as a genuine complex number where I can see the real part and the imaginary part clearly. And I think you can see that now, right? You see the alpha, you see the beta. So here's your alpha, and here's the beta. Yeah. And so I have x of t is equal to c1 e to the alpha t cosine beta t plus c2 e to the alpha t sine beta t. A good homework problem that I could have assigned, should have assigned. I lost my chance though. All right, I was editing. What's that? Do it for extra credit. Yes, you could do this for extra credit. If you could show that this is a e to the alpha t. See, instead of investing your energy in insulting, e to the alpha t sine of, say, beta t plus a phase angle. We could. So the extra credit question is just this, guys. So you can put it at the end of the quiz if you want extra credit. Show you can choose A and phi such that these are the same. I hope that makes sense. What I'm saying is just prove to me that actually you can choose A equals to something and phi equals to something else such that these are in fact the same solution, right? It's just an algebraic rewriting. I mean, there's a theorem at play here which says that the sum of a sine and a cosine, right? If we take a sine and a cosine, both weighted by, one weighted by C1, the other weighted by C2, those in fact form yet another sinusoid of the same angular frequency, in this case 1, but the they're shifted, right? The angle that it starts at, shifted by this phi, this phase angle. Oftentimes, for applications, the thing I just wrote last is really the nicest equation to use for the equation of motion, right? Because if you're going to analyze spring force motion, surely it's much nicer to think about what I'm about to underline in the wavy blue line. Like that, that's a much nicer formula. I can graph that pretty easily, right? What's that look like? Before I do that, let me write down the specific formula for it in terms of alpha and beta, just to be annoyingly explicit. This is A e to the minus b t over 2m, right? Sine of t times the square root of 4mk minus b squared over 2m plus that phase angle. So there you go. That's what the equation of motion is in the weakly damped case or the underdamped case. This quantity right here, we could say omega square root of 4mk minus b squared over 2m. Oh, was that square root? Hold on a second there. Does that square root include the 2m? No. Make it a 4m squared? Well, okay, fine, 4m. You talked me into it. If we bring the 2m inside the square root, it needs to become a 4m squared. And that's actually not a bad idea, because that gives me a chance to simplify this formula again. This is the square root of, what we got? K over m, yeah? Minus b squared over 4m squared, yeah? And that's actually kind of a nice formula to think about. This thing has a name, all right? You would just call it the natural frequency of the system, but people kind of grit their teeth a little bit when you say that, because it's not technically oscillatory motion. I mean, what's an oscillation? If something's really in genuine oscillatory motion, it returns to where it started, yeah? But this is not the case here. The motion here in the underdamped case is bounded by, there's the enveloping curves. There's curves which it's bouncing back and forth in between, namely the dying exponential. So this, e to the minus bt over 2m, that's like the biggest it gets, right? And minus that. So here this is, x equals to a e to the minus bt over 2m. That's the enveloping curve. And so the oscillation starts somewhere with some initial velocity. I mean, you can choose any starting point with any initial velocity. Well, not entirely every. The initial velocity, initial starting point determine what a could be. But once you figure those out, the motion looks something like this, yeah? So if you started somewhere else with a different velocity, you'd get a different looking, motion. But we can kind of pretty well understand what's going to happen in different situations, right? Like if I was here and I started with an upward velocity, et cetera, et cetera, et cetera. All of the possible motions for a given energy are fixed between these two enveloping curves. So why wouldn't you say natural frequency? It's because it's not technically a frequency, because it's not technically an oscillatory motion, right? I mean, it's got, so people tack on the word quasi, just to, natural quasi-frequency. It's almost a frequency. What happens when b equals to 0? We'd have x prime prime plus k over m, x equals to 0. Then the solution is just a cosine square root of k over m t. Oh, did I say cosine? I meant sine. Sine k over m t plus a phase angle. This is the so-called simple harmonic motion, yeah? In that case, the quasi-frequency is a genuine frequency, right? And the exponential bounds become just horizontal lines in that limit. So I suppose you can think of simple harmonic motion as a kind of limiting case of the underdamped case. That's where it fits into this storyline, if anywhere, right? I can't really see sines and cosines coming from limiting cases of the critically damped or the underdamped cases, yeah? All right, any questions? Popular test question, here's a mass, here's a K, here's a B. Determine if the motion of the spring is critically, weakly, or overdamped. Find the energy of the spring. What would the energy of the spring be? Now I'm going back to the physics we already talked about. What's the energy of the spring? Remember we worked this out? The energy is equal to the potential energy plus the kinetic energy, the mechanical system. So what's the potential energy here? So the potential energy would be 1/2 kx squared. We've got the potential energy for a spring. What's the kinetic energy? Well, that's not up for grabs. That's 1/2 mv squared, right? Is this constant? It is not, because we have friction, right? So the energy is decreasing. How is it decreasing? I mean, through friction. If you want me to find the specific rate at which it's decreasing, I can figure that out for you in a couple lines. So check this out. We have, MA, m dv dt, yeah? Plus, what was it? Plus kx is equal to minus bv, yeah? So if I take that and I multiply it by, I think, v squared, multiply by v, I've got m, let's see here, I'm trying to remember, yeah, v dv dt plus k x dx dt, dx dt is v, yeah, equals to minus bv squared. If you tilt your head and squint, you can see that that's ddt of 1/2 mv squared plus 1/2 kx squared by the implicit differentiation rule. So this little calculation right here shows you that, in fact, ddt of the energy is equal to minus bv squared. Wow. Nice. All right. So the change in energy per time is minus bv squared, as you can see. If b is 0, energy doesn't change. It's a conservative system, right? That's simple harmonic motion. But if b is non-zero, that's the rate at which the energy decreases. And you can actually work out the energy as a characteristic of the amplitude at the start, that amplitude, that A. When you actually work it out, if I don't want to, that would have been a good homework problem. Oh well, too late. More extra credit. Yeah, extra credit too. Find E as it relates to A, K, and the quasi-frequency omega. Or does it, maybe it doesn't relate to the quasi, let's say omega naught equal to the square root of K over M. I don't know about that. Well, we'll just figure out the formula for the energy. Let's say that. I don't want to be too precise, because I might say something that doesn't make sense right off the cuff. Let me think about this. Well, let's just say this. Let me make it more specific. Find the energy as a function of time. All right. I will tell you this, you should end up with like a sine squared plus cosine squared, which kind of like makes this actually kind of a pleasant calculation. You do have to find the velocity. How do you find the velocity now that we have the motion? I mean, how do you find the velocity in any of these cases? I found x, right? Velocity is dx dt. So you differentiate. That's it. That's it. Listen, a similar discussion could be had for RLC circuits. If we have a resistor, an inductor, and a capacitor, if you study the differential equation which governs the charge on the capacitor, for example, you'll find out it's a second order constant coefficient differential equation that is much like this. It has positive coefficients, just it's the same kind of math as this. And so again, for an RLC circuit, you have three kinds of possible current flow. You could have underdamped, you could have overdamped, or you could have critically damped, right? You have these three possibilities for the current flow in just an RLC circuit. Now, once you add a current source or a voltage source to an RLC circuit, then that's a more interesting thing. That would correspond to like the solution to a non-homogeneous problem, right? We'll get to that, maybe. Actually, let's get to it now. So I could explain the current next question in terms of, I probably should actually. So here's the next question. So actually, I'll do it over here. So suppose you put Mr. Top Hat in here, and I don't give him a snorkel, and you don't want him to suffocate on the Jello, right? And you give him a stick, and he can push with an external force equals to F naught cosine, cosine, F naught cosine of, say, gamma t. So the question is this: what choice of gamma maximizes the response of, the spring for fixed F naught? So he has a certain amount of force he can push with and pull with, and he's pushing and pulling at the frequency gamma. Which frequency gamma is going to maximize the response of the spring in this situation? So what equation are we facing? Now we're facing the equation mx prime prime plus bx prime plus kx equals to F naught cosine gamma t. Now, we could solve this directly using undetermined coefficients, but this is one of those places where I like to give you an example of complex calculus and how it simplifies our life. All right. So what I'm going to do to this problem is I'm going to complexify it. I'm going to solve the complexified problem, and then we'll find the solution from that. I actually think in the notes have both the uncomplexified solution and the complexified solution. But the complexified solution it's very, very nice. And if we have time, I'll do both, okay? So here's the idea. What I want to do is I want to find a corresponding complex differential equation which allows solutions to the given one as like the real part. So the corresponding complex differential equation that I'm going to look at would just be this: mz prime prime plus bz prime plus kz equals 2. And I need something that has f cosine gamma t as its real part. F naught here is assumed to be a real positive constant. So I think the natural choice is just used f naught e to the I gamma t. See, because the real part of e to the I gamma t is just equal to cosine gamma t, because e to the I gamma t, remember, is cosine gamma t plus I sine gamma t. We've already seen that we had to get into this mathematics to understand, the solution set to the constant coefficient problem. So we've already talked a little bit about this idea. This is Euler's formula. All right, so let's solve this complex differential equation. If we can do it, then the real part of the complex solution should be a solution to my original problem in x, because it's a linear differential equation, right? So if I find a complex solution, then the real and imaginary part are separately solutions. And then there's kind of a play on superposition that's also involved here. But okay, so let's solve this problem. So I'm really just interested in the whatchamacallit, the particular solution. What's the homogeneous solution? I just wrote them down. 1, 2, and 3. Those are the 3 possible homogeneous solutions for this problem. Every single last one of them, right? As long as b is non-zero, what happens as time goes to infinity? If you look at the formulas that I erased, or the one that's still on the board, what happens? Well, you can see in my picture, but look at this. What happens as t goes to infinity? This keeps oscillating back and forth between -1 and 1. It's bounded between -1 and 1. What happens with this? As t goes to infinity, that goes to 0. And the same is true for the critically damped, if you use an application of L'Hopital's rule on the t term, and overdamped. Those are just both exponentials with negative arguments. They go to 0. All right? So as I think about answering the stated question, the homogeneous part of the solution is not going to be the interesting part, right? That goes to 0 after a while. Unless what? Unless I'm in this case. I'm in the b equals 0 case. We already looked at that another day. I solved the b equals 0 case a different day. We found resonance, pure resonance. We found that the particular solution in the case of pure resonance blows up to infinity. We're going to see that that doesn't happen in the current case. If the friction's non-zero, we're not going to blow up to infinity, but there is going to be a maximum choice of applied frequency gamma, which maximizes the motion. All right, so my point in that discussion is just that all we're really interested in is the particular solution. Okay, so naively, we will guess that Z, P, the particular complex solution, should have the form A. Oh, A is a bad choice because I used it in a different sense here. Let me use something other than A just because A's already got some stuff attached to it in this lecture. B e to the I gamma t. If I was going to play the same games I played with you in the real, if I was going to start playing those games in the corresponding complex differential equations, that would be what I would do. I would just try b e to the I gamma t. That would be the natural particular solution. And this is like really, really nice. What's ZP prime? You got yourself I gamma b, e to the I gamma t. Yeah? Chain rule. And ZP prime prime, I gamma squared, b e to the I gamma t. Let me point out something. This is really what? Something I haven't done in our calculations so far, but is oftentimes a very clarifying step to make if you can make it. When you do differentiation or second differentiation of your particular solution, if you can again see it as a multiple of the particular solution again, this is very clarifying if it happens. That doesn't always happen, but sometimes it does, and here it does. See, this is I gamma, right, times b e to the I gamma t, but that is ZP. So we've got I gamma ZP. And likewise, ZP prime prime is minus gamma squared ZP. Pretty neat. I can now plug those into the differential equation, right? Take these, plug them up in here. So I'm looking at m zp prime prime plus bz prime plus kzp equals to f naught e to the I gamma t. What's that actually give me? Well, looks like it's giving me minus m gamma squared plus I gamma times b plus k little b. All of that times ZP. So yeah, what's ZP? That's a complex solution, right? So if I take the real part of the Z equation, I get the X equation. So because of superposition, if I take the real part of the Z solution, I get an X solution. So I need to take the real part of my solution. How do you find the real part of that? What we're looking at is F naught cosine gamma t plus I'll leave the F naught factored out, I sine gamma t divided by k minus m gamma squared plus gamma b squared times k minus m gamma squared minus I gamma b. So what I just did was I multiplied by the complex conjugate of the denominator on top and bottom. When I do that to the denominator, it gives me the squares of the sums of the components. And then I need to multiply it out. So ZP is equal to, looks like we got F naught cosine gamma t times, I want to write the cosine last. So F naught times k minus m gamma squared cosine gamma t. And then I times I gives me a O plus. Looks like a gamma b sine gamma t. See, to find the real part, I take this times that, and also this times that. That's going to give me the real part here. And then divided by k minus m gamma squared plus gamma b quantity squared. Then you got plus I times stuff. I don't really care what's over in the stuff. All right, so now here we need a bit of trigonometry, which is perhaps not widely known. But so the real part, xp is the real part of ZP, again by the superposition I was just talking about. That will be a solution to the original uncomplexified problem. And through the math that I just sketched out there, we know that that's equal to F naught times k minus m gamma squared cosine gamma t plus gamma b sine gamma t, all divided by k minus m gamma squared. Oh, that was gamma squared. Plus gamma b quantity squared. Now my claim is that that is equal to a sine of gamma t plus some phase angle. well, let's call it delta. I don't want you to think it's the same as the phi that I used over there. How do you think A is related? Well, here's the bit of trigonometry that you might not be aware of. A is actually going to be the square root of Pac-Man squared plus Ghost squared if we have x is equal to like Pac-Man cosine plus Ghost, oh man, Pac-Man plus Ghost sine. If you have a sum of two sinusoids, one for cosine and one for sine, unshifted, then the magnitude of when you add them together, it ends up being the square root of the sums of the squares of the coefficients for sine and cosine respective. Would you like this as a third extra credit problem?
Sure.
I don't know.
5 points a question?
5 points a question?
10.
Make it 10?
10 points a question.
I like that.
I think 5 is more reasonable.
How about 7.5? We'll meet in the middle.
How about this one's worth 10, the other two are worth 5? Yeah. It's harder. I mean, I'm saying that you can rewrite, I mean, how do you figure out that it's harder. But it is true. And so the long story short of it then is that the amplitude for my particular solution is just what? It's the square root of, well, okay, so the thing is, I've got this common denominator in both of the both of the things multiplying cosine and sine. So when you square that and square root it, it's just going to end up being the denominator of A. So like just getting to the point, there's going to be a k minus m gamma squared plus gamma b squared down here. But then we also have f naught. There's this f naught multiplies everything. So f naught squared k minus m gamma squared plus gamma b quantity squared. That is square rooted. So that's the amplitude of the particular solution.
So the f naught multiplies the
Yeah, I'm supposed to have an f naught squared over here. The long story short of it, there's an f naught in the front. It pulls out, yeah? And yeah, that f naught multiplies everything. Indeed. Okay, so there is an f naught that pulls out, and oh, look at that. It's the same thing, right? So the pattern is square root of something divided by something. That simplifies to what? F naught over the square root of that. And by the way, A determines the magnitude of the response to the force, right? We're trying to make A as big as we can by doing what? By varying the applied frequency of the pushing force, right? So how do you maximize A given that gamma is the variable? You guys are calculus, students of calculus, you should know the answer to this. What is it? You're like, oh, does that mean we've got to calculate d gamma? d gamma equals to 0. That should give us the critical frequency, right? The frequency which maximizes the response amplitude. So that's what we got to do. That's actually not too bad. I think I can safely erase everything except for the quasi-frequency because I need that to compare to in a minute. I think I can work out the calculus here. So dA d gamma, what is that equal to? So we have F naught over that stuff to the, 3/2 power, right? So minus 1/2, then times what? So, you know what I'm saying? When we differentiate this, it's 1 over the square root function, so we get minus 1/2, whatever's in here to the 3/2. And then the more interesting thing is we differentiate the inside, yeah? Which gives me 2 times k minus m gamma squared times what? Times minus 2m gamma. And then let me be a civilized person and write that as gamma squared b squared. How do you differentiate gamma squared b squared with respect to gamma? 2b squared gamma, right? Now we want all of that to be equal to 0. So the denominator's got nothing to do with it, right? Not to mention the denominator cannot be 0 because it's the sum of squares anyway, right? Actually, the way for the denominator to be 0 would be what? What if b were 0? If b were 0, then the denominator could be 0 if gamma was equal to the square root of k over m. In other words, the weakness to this solution is precisely the simple harmonic motion case. If you think about the mathematics, it blows up in the simple harmonic motion case. That's an exception to our analysis. But we're not in that exception. We're in the current case. And so we just basically, we need this. Can this be 0? If that's 0, then we've got a critical gamma. So looks like we can factor gamma out, right? You got gamma times what? Times 2b squared minus 4 times minus 4m times k minus m gamma squared equal to 0. Am I right? I mean, I tried to multiply the minus 2m times the 2 to give you minus 4m. I left the k minus m gamma squared term alone. I pulled one gamma off each to pull out front like that. So one choice would be what? The DC, if you think about circuits, the DC solution, right? The non-oscillatory one. Just the constant pushing force is a stupid case. That's gamma equals to 0. That's one solution. One possible maximizing amplitude is just the constant pushing force, right? So either gamma equals to 0 or, what's the other case? 2b squared minus 4m times k minus m gamma squared equal to 0. We can solve that. What's that give us? K minus m gamma squared is equal to, looks like 2b squared over 2m, or b squared over m. And so if I can do the math right, which is debatable, let's see here, m gamma squared equals to k minus b squared over m, which then gives me gamma squared equals to k over m. Hey, that looks starting to look almost like I planned this. Minus b squared over m squared. So therefore, the critical frequency, gamma, the amplitude maximizing frequency is actually given to us by the square root of k over m minus, looks like b squared over m squared. These should not be equal. That's fine. And I guess it should be said from the start, we're assuming that gamma is what? Just to make life simpler, we should assume frequency is what? Positive, yeah. You could imagine in a world where you thought about negative frequencies, it wouldn't be crazy. But let's think about frequency being positive. If that's the case, then the second solution may or may not be an honest-to-goodness solution, right? If the square root of the thing we just took is negative, then that's not a positive frequency, right? So in the case that the square root of k over m minus b squared over m squared is an imaginary number, then apparently gamma equals to 0 is the maximizing frequency. But that's the solution to resonance in the case that there's friction, right? So I haven't done anything that... Okay, so you're like, you haven't taught us this method before. Do we need to know it? Not really. You could equally well have done this by taking what? What would you have done if you didn't know my complex trick? You just said xp equals to a cosine gamma t, yeah? Plus b sine gamma t. You plug it in, right? You plug that into the differential equation, work it out. You would again, through that method, still, this would have been the same thing that popped out after you go through the method of plugging in sine and cosine and finding the a and the b. You'd get to the same thing. It just takes longer. But after that, the calculus is the same. So, so I think you can see why I think this is a good example to show you guys in class, but it's not really a very good test question, right? I have assigned this before on a test, though. I have said derive the, the critical frequency. I asked that once upon a time. It was a simpler time. The time is gone. I would not want to grade that at the moment. I do think you guys could do it. Some of you, right? If you're like really done with your studying, eager for the challenge, had already finished everything on the test and was sitting with 30 minutes to tinker, then that would be a reasonable problem. But the stars aligning to make that situation occur for a given student in his class, it's just not typical. So I don't ask that. But I think it's important for you to see this, so I did go through it. Do you guys have any questions about the quiz? I have a few minutes right now. Yeah. So here's a more clear statement of extra credit 3, which is that if x equals to, let's say, a cosine omega t plus b sine omega t, then x is equal to m sine omega t plus delta, where m is equal to the square root of a squared plus b squared. There is a version of extra credit 3 that is divorced from the possibly confusing notation of the problem we were working on. That is it in its most pure form. That is the theorem that if you have a linear combination of sines and cosines with the same frequency, they can be rewritten as a sine of that same frequency shifted with an amplitude, which is the square root of the weights that appear, square root of the sums of the weights which appear with the sine and cosine. Yeah, show that. Exactly, yes. Otherwise, you just write down a piece of paper and that'd be 10 points, and that would, I mean, I'm not averse to that kind of thing, but I feel like there should be some money involved, right? I mean, I'm just kidding, I don't take bribes.